Hi, I'm Simon Collins from AD-Link, and I'm going to talk a little bit about the theme of data to decision. So one of the biggest problems in the military space is timely analysis of intelligence data, both for short-term mission and long-term strategic mission planning and strategic aims. So I'm going to look a little bit about the technology that enables that, both from a processing standpoint and overall from the sort of end-to-end movement of the data. So data, the biggest challenge in defense space. Now, I'm sure a lot of people are sitting there thinking data is not the biggest problem, security is the biggest problem. But actually, as we go through this, what I believe we'll see is that actually having the data and having to move the data around is what presents you with the security problem. So actually, that's a consequence of the first problem, which is there's way too much data. There's a very famous quote from Lieutenant General David Deptula, who was running the ISR department of the US Air Force. And I'll read the quote there. This was from 7 years ago, January 2010. We're going to find ourselves in the not too distant future, swimming in sensors and drowning in data. So 7 years on, he was obviously absolutely right. As we heard earlier, number of sensors increasing dramatically, resolution of sensors increasing dramatically. So there's way too much data. John Boyd had made the observation that you need to be able to collect the data, analyze that data, share the data, and ultimately exploit that data. And in order to succeed, you have to get around that loop faster than your adversary. So really what the military is looking for is application-ready platforms that will enable the systems and the defense community to execute that efficiently and effectively. So the number of sensors, number of assets, huge number of assets out in the field, each of those potentially with many, many sensors and huge bandwidth of raw data coming into those sensors. In addition to the actual mobile assets, there are obviously strategic commands and battlefield commands going all the way back, ultimately, to the intelligence communities. And those intelligence communities are not only looking at the data that's coming off the assets, but they're looking at data and intelligence that's being generated in the wild web. So Twitter, for example, is now one of the sources of intelligence that in real time is flooding in as a result of some of the things that are going on in the urban battle space. So there's an enormous data problem, and it's coming from many, many sources. So the response, cloud computing. And often when I say this, people say, no, the military will never go to cloud. Well, the words on these slides, very wordy slide, and I won't try to read all that. But these words are actually taken from the US Army and the Joint Intelligence mandates on moving to cloud computing. And one of the interesting things I saw is actually the CIA is using Amazon as for its cloud capability, and they have assured themselves of the security of that system. So the words highlighted in red there are the ones I really want to draw attention to. So the single secure information environment. So what does that mean? That means essentially everything is connected together. All of the sensors have to be able to ultimately reach a common point for that intelligence to be, the data to be assimilated and intelligence generated from it. So one of the reasons for wanting to do that is to reach a point of information dominance. So to be able to gather all that, to see multiple views of the battle space and deal with it in real time. And the key there, regardless of location or device, that's a pretty ambitious challenge. And that ultimately is what gives the security or leads to the need for the security. So cloud it seems like the panacea. Unfortunately, as we all know, that real-time connection to the cloud is not always available. Performance of those links is often not great, and sometimes those links are simply not there. So there's something else needed in the mix to achieve this reality. So great, we've got all these sensors, we've got all this raw data, we're going to push it into the cloud, and then the cloud is going to do all the processing. Well, not really. We're still going to need local sensor processing. And we're going to take raw data off the sensors. We're actually going to turn that data into information and intelligence locally. So for example, if you have a radar system, then one of the key things is identifying terrain and identifying objects. And the asset that has that radar is likely going to want to exploit that information locally without that having to go back to the cloud. Target tracking, target identification, IED detection, actually not hitting the terrain. It's kind of important if you're in an aircraft. That raw data, well, we're going to want to process it down into some sensible intelligence that may go back into the rest of the battlefield network, may actually want to store that data, so we'll have all the security problems associated with data at rest and pouring cups of coffee into it as your aircraft is going down, as we heard from previous presenter. So we're going to collect the data, we're potentially going to store it, and that's all going to happen locally in multiple systems within a vehicle or within a platform. Obviously, we're all here because of the technology. ADLink's a board vendor, so I shouldn't say a board vendor, it's a platform vendor. And as we see the technology from the big chip companies advancing year on year, there are a couple of interesting things that happen. First of all, the performance is getting greater, and now we're able to do the traditional applications that don't actually need more performance, able to do those in a lower size, weight, and power envelope. So look at some of the technologies around Intel Atom line and around ARM is starting to become very interesting in this space. And that allows the processing to go to a smaller envelope and onto smaller platforms. So we see some of the things that traditionally required big UAVs are now available on hand-launch UAVs, for example. The converse of that is some of the platforms have a defined swap envelope, and actually that's what the aircraft can lift. So while the application may have collapsed from 6 slots into 1 slot, the platform can still lift 6 slots. So what do you do with the rest of those slots? You can put more functionality into the platform. So whether we're talking about a little ComExpress board, a VPX board, or full-blown LRUs, the whole swap question is very interesting, and different customers, different use cases have a different priority as to where to go with that. So we heard earlier as well about what are we going to do with the data? How are we going to process that locally? And I think one of the things that is really coming from mainstream and is going to have a big impact in military is the whole area of machine learning and artificial intelligence. So we see that really now exploding, and the most obvious place we see it is in autonomous cars. So it was only a few short years ago that people were actually hand-coding algorithms, for example, to try and detect road signs at different angles, in different lighting conditions, when partially obscured. And hand-coding features is very, very time-consuming and actually very limiting because you're only going to achieve a very, very small subset of cases of what that system is going to see. So one of the really big changes there was moving to deep neural net. We heard about that, or deep learning, I should say. We heard about that from a previous presenter as well. So now we go from everything being hard-coded in really hard-coded algorithms to very, very sophisticated machine learning systems. And now we see the cars are out on the road, the many Google, Tesla, Volvo with Uber, all taking what was only a few short years ago science fiction to science fact. We heard that phrase earlier as well. So I really believe that in the defense space, there's going to be a massive capability because if you're doing target tracking, hand-coding the algorithms to do the target detection, sound familiar? That's what's happening all the time. We're looking for a specific type of target. Very, very difficult to upgrade that to look for a new target. Whereas with machine learning, I believe the ability to feed new data and change the target type for acquisition, I think is really ripe for defense. What do we do with all this data? We have multiple sensor processing systems on a platform. And actually, what we want to be able to do is to bring that cloud paradigm onto the platform itself. And this is something called fog processing, or fog computing. So cloud computing, obviously you've all seen the pictures of the clouds in the sky. And the theory of naming is that fog is a little bit closer to the ground. It's a little bit closer to the real equipment. Now, this isn't AD-Link coming up with this name. This is really genuine, used in the outside world, outside of defense. And part of the idea is to move the processing closer to the things that are generating the data. And the fog computing allows secure forwarding of data between the fog subsystems and between fogs, so we can have fog to fog. So if we look at the other end of that, the field command posts are trying to aggregate all this data into something useful to generate situational awareness. And when we look at what's required there, it's very large processing power. So, bigger Xeon servers, 40 gig, 100 gig Ethernet, and also big GPUs. But fog computing applies here as well. And so in those documents that I referred to at the start, they talk of deployed cloud. It's all very well having Amazon on the back end, but actually some of the time you're not going to have that connectivity, or you're not going to want the bandwidth to the back end. So deployed cloud, I heard somebody earlier call it combat cloud, so as a reality. And these ultimately are all going to get fused. So both government and commercial cloud installations are all going to have to be used to harness this data. So we'll look at the whole thing end to end. Obviously, looking at those pictures there, you may have a soldier and an aircraft actually looking at the same target, the same piece of the battlefield, and actually you want to be able to recover all of the information about those common areas and actually utilize that information to get from the raw data ultimately to a decision of what are we going to do about that. Fog computing, it's based on open standards. So in the telecom space, you'll see the phrase mobile edge computing. It's also called fog computing. They're essentially the same thing. So it's based on open standards. It's real-time performance. It's got to be reliable. So regardless of whether you're in the battle space or in some of the industrial IoT arenas, it's essentially the same problem. You want reliability, you want security, and you want to be able to ensure that your data is going only to the place it's intended to go. Nothing is coming in to change that. And this technology is really being driven by the commercial market. It's been driven in the telco space. I think the summary, as ever, the industrial challenges are similar to those faced in the military. I think we're going to see those technologies of secure cloud and fog computing actually being the things that enable that larger vision of being able to have ubiquitous sharing of data where it's needed, when it's needed. And I think the local processing, I think we're really going to see the benefits in the next generation of systems that are deployed, machine learning, artificial intelligence, to get away from hard coding everything and actually start to be able to be much more dynamic in the way that those systems behave. So commercial technology is going to drive the advances. We've seen that many times before. And ultimately, the way to harness that is through open standards, both for the hardware, for the software, and the middleware. Thank you.